Alright, so we made to chapter 4. It's a long chapter, but some of the sections aren't that long. And section 4.1 is on the friendly and short side. And it's completely review. Sections 4.1 and 4.2 are reviews of the rules of exponents. 4.1 is definitely easier than 4.2 because in section 4.1 we only deal with positive exponents. In section 4.2 we have negative exponents and zero exponents, which makes that section a little bit harder, but it's review. Ultimately, we get into fraction exponents. So we have to be real comfortable working with just the basic rules of exponents without fractions so that we can transition into the fraction exponents pretty smoothly. So I'm going to make up just a couple of review problems before we get into the section. The section's really not terribly hard, but I just want to review a little bit some of the rules. So one of the rules I'll say is, I'll call it the multiply to add rule. I doubt that this is the real name of the rule, and I'm not sure the rule even has a name. But what it allows me to do is if I have a multiplication problem, like x cubed times x to the fourth, this is a multiplication problem, but I don't have parentheses between the x's, or a times sign. I could have written the problem like this to signify multiplication, or I could have written the problem like this to signify multiplication. But when you have two letters next to each other without a symbol, it's an implied multiplication. So all three of these problems are multiplication problems, and they're multiplication problems with like bases. I'm multiplying an x cubed times x to the fourth, and in each one, like in the x cubed piece, the x is the base, the 3 is called the exponent. In the x to the fourth piece, the x is the base, the 4 is the exponent. And this rule, the multiply to add rule, has to do with multiplying terms with like bases or equal bases with the same base. So I'm multiplying two terms with the same base, and when you multiply terms with the same base, you add the exponents. So this problem can be solved by, instead of writing two x's each with its individual exponent, write one x and add the exponents. The answer to what x cubed times x to the fourth is x to the 7th. And I can show you why it works. If I wrote x cubed without its exponent, I'd have 3 x's being multiplied. I don't need the times sign, but I can have them. And if I wrote the x to the fourth without its exponent, I'd pick up another 4 x's being multiplied. So if I expanded x cubed and x to the fourth and wrote them without their exponents, left the multiplication, I'd have a series of 7 x's being multiplied, and 7 x's being multiplied is equivalent to x to the 7th power. That wouldn't work if I gave you this problem. If I asked you to multiply x cubed times y squared, this can't be simplified because the bases aren't the same. You can't add the exponents and get something to the 5th. So this cannot be reduced. In order to make two terms into one term, when you're multiplying using the multiply to add rule for exponents, the bases have to be the same. It's almost easier to do the rules with letters than it is numbers, because when I have numbers, it's easy to make a mistake. So if I gave essentially the same problem but changed the x's to 2's, if I did 2 cubed times 2 to the fourth, all of a sudden it doesn't look to be the same style of problem, and students often they multiply the 2's when they write this with 1, 2. So the rule applies. This is going to be, I'm multiplying each term. The first term has a base of 2, and an exponent of 3. The second term has a 2 for a base and a 4 for an exponent again. So the bases, they have the same bases. And you can multiply terms that have the same bases. And to multiply terms when you have the same bases, you don't really multiply, you just add the exponents. If I wanted to do this, this is the same as 2 to the 3 plus 4, which is 2 to the 7th power. A wrong answer to write 4 to the 7th power. The nice thing about when we're dealing with numbers, it's easy to check my answer because I can take the original problem, toss it on my calculator, figure out what it equals to, and take what I think the right answer is, put it on my calculator, and see if I get the same result. With the x's, I didn't really need the time sign between the x's, but with the numbers, I should put the time sign between. Otherwise, my calculator might get confused, and it might just be confusing. So I'll show you that these are equal, but 4 to the 7th isn't. So the initial problem that I just completely made up, it's not in the handout, is 2 to the 3rd power times, and then 2 to the 4th power. So this is supposed to equal 128. If I look at what I say is the correct answer, 2 to the 7th power, I do 2 to the 7th power, it's also equal to 128. And if I look at what I say the wrong answer is, 4 to the 7th power, because it doesn't equal 128, it's not even close to 128, it's way wrong. So the important thing about the multiplying terms with the same base is when you do the multiplication, you're not really multiplying, you're adding the exponents. The thing about this rule, it's not limited to 2 terms. I could have 3 terms being multiplied. For instance, if I did, I'll do something with numbers just because I can check. If I did 3 times 3 to the 2nd power times 3 to the 2nd power, there's 3 terms here. The first term has a base of 3, and it doesn't look like it has an exponent, but every term has an exponent. It's just we don't always write it. If no exponent is written, it's assumed to be 1. And for this, both the second term and the third term that I'm multiplying, maybe factor would be a better word, but term I'll live with, they both have a base of 2, a base of 3, and an exponent of 2. Because each of the pieces here that I'm multiplying has the same base, I could use the multiply to add rule, and this is going to equal 3 to the 1 plus 2 plus 2 power, which is 3 to the 5th power. I can do this on my calculator and this on my calculator to show you that these are really truly equal. So I'm going to enter the original problem that I completely made up, 3 to the 1st power, I shouldn't have entered the 1 there, but it's not wrong to, times 3 to the 2nd power times 3 to the 2nd power. So this by itself is equal to 243. And what I say it's equal to is also 243. So we'll get a reasonable amount of practice with this rule when we get into the section. So that's one of 3 rules that we have to remember. And it's probably the easiest of the 3 rules. The second of the 3 rules, I'll do it with numbers first. I'll say raising 1 base to 2 powers, or 2 exponents. Powers and exponents can I use interchangeably in this chapter. For this, you multiply the exponents to simplify. These kinds of problems almost always have a parentheses. with an exponent inside and outside the parentheses. So this is an example of raising one base to 2 powers. How about this? 2 to the 3rd power squared. So here the base is 2, and the exponents that apply to the base are 3 and 2. So I have one base that has 2 exponents that apply to it, and my rule says if I have one base and 2 exponents that apply to it, I can get that 2 exponents down to 1 exponent if I multiply the exponents. So I claim that 2 cubed to the 2nd power is equal to 2 to the 6th power. Notice in none of these exponent rules am I going to change the base. So let me show you that this actually works. So I'm going to enter the original problem, 2 to the 3rd power and then squared. So the problem that I initially made up is equal to 64. It best be the case that 2 to the 6th is 64 as well. And if I do 2 to the 6th in my calculator, I get 64. So I can see that rule works. It works for variables as well. Like if I had y to the 5th power to the 4th power, this has one base, y, that has 2 exponents that applies to it, and that's going to be y to the 5 times 4th power, which is y to the 20th power. Where we have to get careful with this rule is this rule only applies when the inside of a parentheses has straight multiplication, and it doesn't apply when we have addition inside a parentheses. So I'll show you a more complicated version of a problem that this would apply to, and I'll do it just with numbers. If I gave you something like this, 2 to the 3rd times 5 to the 2nd power all to the 4th power, this is going to be an insanely large number. But this still has the rule that we just wrote. It applies to it because if inside the parentheses there's times, the rule applies. And I can rewrite this as 2 to the 3 times 4 power, because 3 and 4 have the 2 has 2 exponents that applies to it, and the 5 has 2 exponents that apply to it. So I could expand this rule as long as there's only multiplication inside the parentheses. If I have, no matter how many bases I have inside the parentheses, if there's no adding or subtracting, this is going to be equal to the original problem. So I'd say, this might even blow my calculator up, but that this 2 to the 12th, 5 to the 8th is going to be equal to this. And again, I'm going to show you on my calculator that these two are the same, so I've correctly applied the rule that I'm talking about. So entering this first, parentheses 2 up arrow cubed over times 5 squared, parentheses all to the 4th power. So the original problem is equal, oh my gosh, 1, 2, 3, 6, 8 zeros and a 16. So 16, then 1, 2, 3, 4, 5, 6, 7, 8 zeros. So 1,600,000 if I did that right. I'm going to do the same thing with this. So I'm going to go 2 up arrow 12th power times 5 up arrow 8th power, and I get the same 16 followed by 8 zeros because these are equal to each other. The rule's going to work when I have letters mixed with numbers, as long as I have straight multiplication inside of parentheses. Like if I had something like this, 3x to the 4th power all squared, because inside the parentheses there's only multiplication, this problem above and this problem are essentially, this can reduce the same way. And how do I reduce? I'm going to multiply the exponents by the 2 outside the parentheses. The 3 has an exponent of 1. That's not written, but it's assumed. The x has an exponent of 4 that is written, and this whole thing is going to reduce to 3 to the second power times x to the 8th. Because 3 to the second power is 9, it reduces to 9x to the 8th. So both of these are kind of extensions of the rule that if I have two exponents that apply to a single base, one base, two exponents that apply, you multiply the exponents. But that rule doesn't apply when you have pluses or minuses. For instance, I'll do something with numbers that, like if I had something like this, 2 squared plus 5 squared to the 4th power, you'd like to extend that rule and say that this equals to 2 to the 8th power plus 5 to the 8th power, but it doesn't work. So let me show you the original problem that has a plus between the terms. If you see what it equals to. So I have 2 squared plus 5 squared all to the 4th power. So the original problem equals 707,281. For this to be correct, this also has to equal 707,281, and it's not gonna. If I do 2 to the 8th power plus 5 to the 8th power, I get 390,881. So it doesn't work, the rule. The rule only works for if you have more than one term with two exponents, when there's times between it. When there's plus between it, it doesn't work. Similarly, if I gave you something like this, x plus, how about x squared plus 3 squared? This will not reduce. This does not equal, even though you'd like it to equal this, it doesn't equal x to the 4th plus 3 squared. It isn't the case where I can just multiply the exponents. I can easily tell you what this does equal to. The correct way to simplify this is foiling. The correct way to reduce this particular problem is FOIL, because I can write it without the exponent. I can say this is x squared plus 3 times x squared plus 3, and then FOIL. Firsts are x squared times x squared, which is x to the 4th. Outers are x squared times 3, which is 3x squared. Inners are 3 times x squared, which is 3x squared. And the last are 3 times 3, which is 9. So this piece right here, it doesn't equal x to the 4th plus 9 or x to the 4th plus 3 squared. It actually equals x to the 4th plus 6x squared plus 9, which is 3 squared. So there's a danger into getting too comfortable with these rules because they're so easy to use them when you can't use them. So the rule that allows me to multiply exponents works without any sort of complexity when you have clearly one base with two exponents. Still works if there's straight multiplication inside a parentheses and an exponent outside. You can multiply the exponents inside the parentheses. But once we have pluses between the terms or minuses between the terms inside a parentheses, you can't multiply the exponents and simplify. You have to get into something that's foiling or more complex than foiling, but it's a big, messy problem. This problem right here, to do an expansion right without the parentheses would be a complete nuisance to do, and I wouldn't try to do it right now. So that's the second of 3 rules. I don't know if it's the hardest of the 3 rules, but it could be. The third of the 3 rules is dividing terms with the same base. And what I normally do is I subtract the exponents. And leave where the larger exponent is. And that's really written horribly right now, but it's going to hopefully become clear in a second. So here's an example. I'm dividing terms with the same base. 2 to the third power over 2 to the seventh power. So I'm dividing terms with the same base. Each of the terms has a base of 2. They have exponents of 3 and 7. When you're dividing terms with the same base, you subtract the exponents. The exponents are 7 and 3. I'm going to subtract the exponents. 7 minus 3 is 4. Because the bigger exponent is in the denominator, when I do that subtraction, I'm going to leave my exponent in the denominator. I can't write a fraction without a numerator, so I'm going to leave a 1 in the numerator. So I claim that these two are equal, and I can show you that they're equal because they don't have letters. I can do them on my calculator. So the initial problem is 2 to the third power over 2 to the seventh power. The initial problem reduces to 1/16. If I look at what I say the answer is, fraction 1 over 2 to the fourth power, it also reduces to 1/16. If I would have written 2 to the fourth not as a fraction, it would be wrong if I said 2 cubed over 2 to the seventh equals 2 to the fourth and didn't make a fraction, because the initial problem is 1/16. That not being a fraction is 16, and 16 doesn't equal 1/16. If I gave you a problem like this, 3 to the fourth over 3, it's another problem where I'm dividing terms with the same base. The base in the numerator is 3, the exponent is 4. In the denominator, the base is 3. There's no exponent written, so there's an implied 1. I'm going to subtract the exponents to simplify this. 4 minus 1 is 3. Now I'm going to leave the 3 in the numerator of the fraction because the bigger exponent 4 is in the numerator, which forces my 3 to be in the numerator, and I don't need to write a fraction anymore because this 3 cubed is in the numerator, and what I have left in the denominator is a 1, and I don't need to write a fraction with a 1 in the denominator. So again, I can show you that this and this are the same. It's super easy to show. So on this calculator, if I did 3 to the fourth power over 3, the initial problem is equal to 27. And the answer that I have, 3 to the third power, is also equal to 27. This rule expands to letters, and as long as I have straight multiplication in a numerator and a denominator, I can use this rule all day. Once I have adding or subtracting, the rule can't be used so nicely. So for instance, if I had something like this, x to the fifth over x to the ninth, the rule can be applied there because I have term in the numerator and the denominator with the same base. I'm going to subtract the exponents. 9 minus 5 is 4. And in this problem, the exponent needs to be left in the denominator because 9 is bigger than 5. And I can't write a term without a numerator, so I'll leave a 1 behind. If I made a problem like this, y to the sixth over y squared, same rule applies. I'm dividing with like bases, so I subtract the exponents. Here, the bigger exponent's in the numerator. When I do the subtracting, if I subtracted right, I'll get y to the fourth. I don't need a fraction anymore because that y to the fourth winds up in the numerator. Technically, what I have left is a 1 in the denominator, but I don't need to write a fraction with a 1 in the denominator. I can blend this rule. I could do something like this, x to the sixth, y to the fifth over x to the eighth y. Because there's only straight multiplying, I can use this rule perfectly to reduce my exponents. I do the x's separate from the y's. For the x's, I subtract the exponent. 8 minus 6 is 2. The x needs to wind up in the denominator because the larger exponent on the x is in the denominator. For the y's, I need to leave the y in the numerator because the larger exponent, the exponents on the y's are 5 and 1. The denominator had a 1 that wasn't written. For the y's, I'm going to get a y to the fourth in the numerator. This rule doesn't apply when you have adding or subtracting. For instance, if I made a nice problem with numbers so I could show you that it doesn't work, if I gave you something like this, 2 to the third power plus 3 squared over 2 to the fifth power plus 3, you can't reduce this. This just can't be reduced. The plus makes the rules not work. It would be super common for students to go, well, I can reduce that to be 2 squared in the denominator because I can subtract those exponents, and 3 to the first power in the numerator. If I do this on my calculator and this on my calculator, they're just not going to equal to each other. So if I did this initial problem of fraction 2 cubed plus 3 squared over 2 to the fifth plus 3 to the first, the initial problem equals 17 over 35. For my answer to be correct, it has to also equal 17 over 35, and the answer that I wrote that I know is the wrong answer, 3 over 2 squared, equals to 3/4. So each of the rules that we're learning, the dividing and subtracting exponents, the raising one number to 2 powers, and multiplying the exponents, it only works if you're straight multiplying. And even the first rule, something like this, 2 cubed plus 2 to the fourth, that doesn't equal 2 to the seventh. These can't be combined by the rules of exponents. Like the difference between this, 2 cubed times 2 to the fourth, which is 2 to the seventh, that isn't 2 to the seventh. If you said this was 2 to the seventh, you'd be wrong. This is wrong, and this also can't be reduced. Once you have a plus between the terms, these rules don't work, because if you see here, 2 to the third power plus 2 to the fourth power, this equals 24, but 2 to the seventh power equals 128, so it doesn't work. So every one of these rules, the multiplying to add the exponents, the raising a power to 2 exponents to multiply the exponents, and the dividing to subtract the exponent, each one of those 3 rules will never work in a problem that has a plus or minus between the terms. Once I see any addition or subtraction, I just throw these rules away. They don't work. But in the section, there aren't any pluses or minuses, so I just do basic examples of these rules. Okay, so that's everything I wanted to say about the rules, and maybe even a little bit more of what the rules are, when you can and can't use them. And now I'm just going to do all the even problems in the section, and it's going to go really fast. Hopefully you're able to work this section and get way ahead of me on the video. You might be able to do the whole section now without even watching my lecture, and that would be fantastic. So I'll just do all the even problems, try to mention the rule that applies. The rule that applies here is I'm multiplying terms. The first term has a base of z and an exponent of 4. The second term has a base of z and an exponent of 2. So I'm multiplying terms with the same bases. To multiply terms with the same bases, you add the exponents, and the answer to problem 2 is just going to be z to the 6th power. And that's all there is to do. Question 4, it has similar. The first term has a base of b and an exponent that's clearly a 2. The second term that I'm multiplying has a base of b, an exponent that's not written, but it's a 1. So both the problems on this first page, problems 2 and 4 from section 4.1, use the rule if I'm multiplying terms with the same base, I don't change the base, I add the exponents. And they're all problems where I would probably just write the answer down. I wouldn't show any work. The step that I showed in problem 2, the step that I showed in problem 4, I would never show those. I'm just emphasizing that's what I'm doing. Problem 6 is dealing with numbers. And again, it's the same rule. The first term has a base of 3 and an exponent of 2. The second term has a base of 3 and an exponent that's not written, so it's assumed to be 1. I can use the rules of exponents and say this is 3 to the 2 plus 1 power, which is 3 cubed. Generally, I'll never write a number with an exponent if my calculator can do this without giving me, like that 1.6 billion, because I don't want to write, 8 zeros. If it's easy for me to write, then I'm going to figure out what it is on my calculator and write it down. So, although 3 cubed is a nice answer, 27 is a better answer. And every time I have a number with an exponent, I'm going to try to figure out what it is. And if it's not a nuisance to write it down, I'm going to write that down. But like I said, that time that I wrote the 16 followed by 8 zeros, that I would consider a nuisance, and I wouldn't write that down. So 8's still an example of the rule. I'm multiplying this time 3 terms with the same base. I'm going to add the exponents. The exponents are 4, 2, and 1. In all of these rules, the bases don't change. My answer to problem 8 is going to be y to the 7th. (10) and 12 are the first ones that use the divide rule. Each one of these, I'm dividing terms with the same basis, so I subtract the exponents, and I have to make sure to either write my answer as a fraction or not, depending if the larger exponent's in the denominator. In both problem 10 and 12, I have to leave the y in the denominator because the bigger exponent is in the denominator. So my answer for both 10 and 12 is going to wind up being a fraction. If you didn't write your answer as a fraction, you can write an answer with a negative exponent, and that's just not desirable. I haven't got into negative exponents yet. Similarly, problem 12 is really just a copy of problem 10. It's no different. It's dividing 2 terms. Their bases are y's. When you're dividing terms with the same base, you subtract the exponents. You leave the letter where the larger base or exponent was, the larger exponent, and this was a 5, so we'll leave this in the y in the denominator. I can't write a fraction without a numerator, so I'll have to 1 behind in the numerator. 14 and 16, I'm dividing terms with the same bases. The bases aren't going to change. I could do these problems without using any of the rules of exponents because the numbers are small. I can make 3 cubed 27. I could do this on this one. 3 cubed over 3 squared is 27 over 9. And I know that 27 over 9 is 3. There wouldn't be anything wrong with doing it that way. It's completely right. If you're comfortable and you know the exponents quickly, or if you just want to do that on your calculator, you don't need to use the rules of exponents. But it's in this section because you can use the rules of exponents. And in problem 14, if I'm using the rules of exponents, I'm subtracting the exponents. And this is the first one where it doesn't need to be a fraction, and it shouldn't be a fraction. The 3's going to wind up in the numerator because the bigger exponent's in the numerator. I'm not going to write a fraction like I did for the last 2. When I subtract the exponents, I get 3 to the 1st power. And for my answer, I'm not going to write an exponent when the exponent is 1. I'm just going to write the number 3. Similarly, 16, if I knew my powers and could reduce fractions without my calculator, if I did this on my calculator, I could do this. I can say this is 3 over 81, because 3 to the 4th is 81. I can divide 3 by 3 and get 1. 81 divided by 3 and get 27. That can be done without a calculator, without using the rules of exponents. But I would either use the rules of exponents or use my calculator, because sometimes I make mistakes when I try to do things by hand. So this is a similar problem to the one above it, but it's different because the bigger exponent's in the denominator. The 3 in the numerator has an implied exponent of 1. Well, if I'm using the rules of exponents, I need to subtract the exponents because the larger exponent's in the denominator. I need to have a fraction answer with a 1 in the numerator. And this reduces to 1 over 3 cubed. And 3 cubed is 27. So this is going to be 1 over 27. Again, I could have just did this on my calculator. I did 3 over 3 to the 4th. And it had told me it's 1 over 27 without using the rules of exponents. But once the problems have letters, you're bound to the rules of exponents. The next few problems, I have one base, two exponents, so I'm just going to multiply the exponents. In problem 18, to clear the parentheses, the base of y has an exponent of both 3 and 4. I multiply the exponents. The answer to this problem is going to be y to the 12th. For 20, I have one base, b, with two exponents, 2 and 5. To simplify that, I multiply the exponents and get b to the 10th. 22 and 24, since there isn't any adding or subtracting, I can multiply all the exponents by 3. If I wanted to on 22, I can consider this x to the 1, y to the 1, z to the 4th, all cubed. And because there's no adding or subtracting, I can cube by just multiplying the exponents by 3. So this would be x to the 1 times 3, y to the 1 times 3, z to the 4 times 3. And my answer is going to be x cubed, y cubed, z to the 12th. If I was doing this, I probably wouldn't have written it like this. I would have simplified straight from here, and I would have just attached the exponent. The x, I didn't have an exponent written. The y didn't have an exponent written. I'll just give it that 3, because I'm kind of multiplying 1 times 3 without showing it. And then for the z, I'd multiply and still get the same answer. So you don't need to show the steps here that I'm showing, and I generally wouldn't. For instance, if I was doing problem 24, both the 3 and the x have exponents of 1. So you're going to go, this is really what the problem is. If you're showing the rules of exponents, I'm going to go, this is 3 to the 1 times 4, x to the 1 times 4, y to the 5 times 4. I can multiply all the exponents by 4 because there's no adding or subtracting. Practically, I don't show the 1. If I was doing this, I would just raise 3 to the 4th power, raise x to the 4th power, and multiply the exponent on the y. They both take you to the same place. In my answer, I'm going to usually not write a number with an exponent unless when I simplify it, it gets out of control big. So 3 to the 4th power is 81. That's not out of control big. So in my answer, I'm going to write 81 for the number. I'm not going to write a number with an exponent if I don't have to. X I'm going to have to the 4th power. Y I'm going to have to the 20th power. Over halfway through this section, 26, I have to be ultra careful with that negative. It's if I'm going to use the same strategy that I did and raise the negative 2 to the 4th power and the x to the 4th power, the negative needs to be in a parentheses. So whether I'm attaching exponents of 1 to the x and the negative 2 or not, when I multiply this out, if you don't leave the 2 inside a parentheses, then you'll probably get the wrong sign when you go to use your calculator, because negative 2 to the 4th power means negative 2 times negative 2 times negative 2 times negative 2. It means positive 16. If you don't put the negative 2 in a parentheses, when you go to use your calculator, you'll get a negative 16. I wouldn't use this strategy for rewriting this. I would go like this. I would say this is negative 2 to the 4th power, x to the 4th power, y to the 3 times 4th power. So the number and the letter didn't have exponents. I'm just going to attach the exponent of 4 to them. I'm going to use my calculator for the negative 2 to the 4th. So negative 2 to the 4th is 16, positive 16. If you didn't put the negative 2 in a parentheses, you'd get a negative 16, which is wrong. And for the y, I'm going to multiply its exponent. This is the only, well, the best correct answer. You could write negative 2 to the 4th power, but that seems silly to do. 28's back to the dividing with the same bases. So in 28, I'm going to reduce the a over a squared and the b cubed over b and write them in one fraction. For the a's, I'm subtracting the exponents on the letters. The letters have exponents of 1 and 2. I'm going to subtract the exponents on the a. Because the bigger exponent is in the denominator, I'm going to leave the a in the denominator. Its exponent's going to be 1. So instead of writing the 1, I would probably just write a. For the b's going to wind up in the numerator because the bigger exponent, 3, is in the numerator. I'm going to subtract the exponent of 3 that I see, the 1 that's implied, and get b to the second power. If I was writing an answer to 28, it would probably, best answer would be b to the second over a. Now the problems are getting to the hard variety. On 30, I would probably simplify the numerator first. Because the y's in the numerator, I have 2 bases and 2 exponents. In the numerator, I'm going to add the exponents to make it from 2y's to 1y. And now I have a simple fraction. It has same bases, so I subtract the exponents. Because the bigger exponent's in the denominator, my answer has to be a fraction, and the exponent needs to wind up with the letter in the denominator. 32 is the big step up in difficulty. I have to get rid of this first. So the first thing I have to do is get rid of this exponent. So I have to simplify this first because it has an exponent outside of it. And to simplify it, I'm going to do this. I'm going to go negative 4 cubed x cubed y to the 2 times 3. I'm going to leave it all in a parentheses next, and I still have the negative 2xy alone. So I'm just dealing with the exponent outside the first parentheses. I can't combine the 2 parentheses because I have to do exponents before multiplication. If I multiplied like the negative 4 and the negative 2 first, I'd be doing multiplication before exponents, violating the rules of the order of operations. So first parentheses had an exponent. I'm getting rid of the exponent. Let me do the negative 4 cubed. So negative 4 cubed is negative 64. So I get negative 64 x to the third y to the sixth times negative 2xy. So they're negative numbers, but there isn't any adding or subtracting. So I'm just going to multiply like terms now. To simplify this, because multiplication is commutative, the multiplications that I need to do are negative 64 times negative 2, x cubed times x, and y to the 6 times y. So to get to my answer, I need to simplify the 2 numbers, the 2 x's, and the 2 y's all down to 1. And there is no rules of exponents for multiplying 2 numbers. I'm just going to multiply those numbers. So negative 64 times negative 2. They don't have exponents. It's just flat out multiplication. Negative 64 times negative 2 is positive 128. For both the x's and the y's, I'm going to add their exponents. And the x and y that didn't have an exponent, there was an implied 1. So my answer to this is going to have an x to the 4th power and a y to the 7th power. So it's way more complicated. It's a big step up in difficulty, but it doesn't involve any new rules. It does involve orders of operations, doing exponents before multiplication, and then it has traditional multiplication that doesn't use the rules of exponents. So it has a couple subtleties in it. 34 is also, I have to do the exponents first. So you can't multiply when you have exponents outside parentheses. So I'm going to get rid of the exponent outside the first parentheses, make it x to the 2 times 3 power y cubed. And then in the second parentheses, I'm going to make it 2 to the 4th. Doesn't need to be in a parentheses because the 2 is not negative. X to the 4th, y to the 2 times 4. So that would be a nice way to reduce in terms of getting the exponents done first. And this simplifies to be x to the 6th, y cubed. I know 2 to the 4th is 16, but if you don't, 2 to the 4th is 16. X to the 4th, y to the 8th. Now multiplication is commutative. I'm just going to multiply the like pieces. So I'm going to have 16 times x to the 6th times x to the 4th times y cubed times y to the 8th. And then I'll get my answer. The 16 is just going to be part of my answer. It's not going to have anything to cause, nothing to multiply by to change it. For the x's, I'm going to add their exponents. For the y's, I'm going to add their exponents. That might be as hard as it gets. It looks like the next few problems aren't as hard. It looks like they're division problems again. And, well, maybe they get hard. This to problem 36, there's no adding or subtracting, so I can reduce each separately. I'm going to treat this like 3 problems. The first problem I'm going to treat as 12 over 24. The second problem I'm going to treat as x squared over x. The third problem I'm going to treat as y squared over y. The x's and the y's that don't have exponents have implied ones. 12 over 24 reduces. I can reduce it without my calculator, but my calculator doesn't make as many mistakes as me. 12 over 24 reduces to 1/2. I know I certainly need a 2 in the denominator. If the rest of the fractions reduced and they all wound up in the denominator, then I'd have to have a 1 in the numerator. I don't think I'm going to wind up needing that 1 in the numerator. It wouldn't be wrong to have the 1 in the numerator, but it turns out not to be necessary because I'm going to get an x and a y in the numerator. When I simplify the x's, I subtract the exponents, and I get x to the 1st power. When I subtract the exponents on the y's, I get y to the 4th power. So if I wanted to write everything, 12 over 24 reduces to 1/2. X to the 2nd over x to the 1st reduces to x to the 1st in the numerator. Y to the 5th over y to the 1st reduces to y to the 4th in the numerator. I can write more than I need to, but the best answer would just have an x, y to the 4th in the numerator, and a 2 in the denominator. I wouldn't show the 1 from the 1/2, nor the 1 as the exponent of the 2, of the x. 38. This rule of multiplying exponents applies to fractions as well, as long as there isn't any adding or subtracting inside the parentheses. So I'm going to extend that rule to the fraction. I'm going to cube the 3 and multiply the exponent on the y by 4, or by 3. For an answer, I'm going to get y to the 12th in the numerator. The 3 started in the denominator. I'm going to cube it and leave it in the denominator. And 3 cubed is 27. And again, anytime a number can be written without its exponent, it's not a nuisance to write what it's equal to. I'm going to write that number without the exponent. So almost done with this section. Hopefully you're feeling good about it. You need to be really comfortable with this section in order to handle the next section that has 0 exponents and negative exponents, and then to make the big step up to problems that have fraction exponents. 40 is just a more complicated version of the same style of problem as 38, as is 42. So I'm going to multiply the exponent on the x, and I'm going to attach the 3 to the 3 and the y. I could technically write exponents of 1 with the y and the 3 and multiply the exponents, but that's not necessary. For the x, I'm going to multiply its exponent and get x to the 6th power. 3 cubed I just did. It's on my calculator staring at me. It's 27 and y cubed. So the answer should be x to the 6th over 27 y cubed. 42 is just a bigger version of 40, which was a bigger version of 38. No adding or subtracting, so I can just multiply the exponents on the letters. So it's x to the 2 times 4. I'm going to raise the 3 and the y to the 4th power and multiply the exponent of the z by 4. 3 to the 4th power, I know what it is, but if you don't, 3 to the 4th power is 81. So in my answer, I'm not going to write 3 to the 4th, I'm going to write 81. In the numerator, I'm going to write x to the 8th power. In the denominator, I'm going to have 81 y to the 4th, z to the 12th. So you just need to get super comfortable using the rules how I used them in this section before you move on to 4.2. And then in 4.4, you're going to feel like you're going to forget all these rules once the exponents turn into negative fractions. But everything we get, no matter how complicated the problem looks, these are just the rules of exponents we're going to use for this chapter. It's just going to feel harder as the problems get more complex. Once we get negative exponents, they'll be a little bit harder, but they're kind of easy to deal with when we don't have adding or subtracting in a problem. And then once we get the fraction exponents, that's the next level of difficulty. But if you have a good foundation in this section, if you can do these problems and look at the problem and know immediately what to do, then you should be able to do well in section 4.2 and in section 4.4, which are kind of the meatier exponent sections. Alright, so that's the whole section. Hopefully you can do all the odd problems in this section and you feel good about it, and then you can move on to 4.4, and this was like hopefully not that long of a video for a change.